You know, when you see a perfect smile, it's easy to think it's just about aesthetics. But underneath it all, it's this amazing mix of biology and pure physics. Today, we're going to pull back the curtain and look at the basic mechanics that let orthodontists move teeth with such incredible precision. And it all starts with solving one major problem.
So here's the central puzzle. If you need to move a tooth from point A to point B, how do you get there without it just falling over? How do you keep it perfectly upright and controlled? This is the fundamental challenge that every single orthodontic treatment has to figure out.
Because if you just push on the part of the tooth you can see, the crown, with a single force, something very predictable happens. It tips. It just pivots around a point somewhere down in the root. And that kind of uncontrolled tipping, that's almost never what you actually want.
To get around that natural tipping, orthodontists have to be masters of physics. Seriously. And for us to understand how they get that control, we need to get a handle on three key concepts: forces, moments, and a really clever idea called a couple.
All right, first up is force. This one's pretty straightforward. It's the push or the pull that gets an object moving. In orthodontics, we're talking about really light forces measured in just grams or ounces because we're working with living tissue. It's all about that gentle, continuous pressure. Now, here's where it gets interesting. Every single tooth has a balancing point, what we call the center of resistance. The best way to think about it is like a fence post in the ground. If you push on the top of that post, it doesn't pivot right at the ground, does it? It pivots somewhere in the middle of the part that's buried. It's the exact same for a tooth. Okay, so if you're applying a force to the crown, which is way above that center of resistance, you're not just pushing the tooth. You're also creating what's called a moment. A moment is just the physics term for the tendency of that force to make something spin. That moment is the unwanted tipping we saw a second ago. It's a rotational side effect we have to get under control.
So how do you fight back against that unwanted rotation? Well, this is the orthodontist's secret weapon, the couple. A couple is just a pair of forces that are equal in strength but are going in opposite directions. Think about turning a steering wheel with two hands. The push and pull cancel each other out in terms of moving the wheel forward, but what you're left with is pure turning force. That pure rotation is the key to countering the tipping.
So we've got the tipping moment from our main force, and we've got the counter moment that we're creating with our couple. The secret recipe for moving a tooth exactly where you want it to go is all about mastering the ratio between those two.
And this is the absolute key takeaway. How a tooth moves comes down to a battle between that natural tipping moment, which we'll call MF, and the controlled counter moment we create, MC. The ratio between these two opposing forces dictates, well, everything.
Let's walk through it. Case 1. What if we have zero counter moment? We're just pushing on the tooth. Well, the MC/MF ratio is 0. And the result? You guessed it, uncontrolled tipping. The tooth just pivots around its center of resistance. Now, let's add in just a little bit of that counter moment from our couple. Not enough to fully cancel out the tipping, but enough to fight back a little. The ratio is now somewhere between 0 and 1. This gives us controlled tipping. The center of rotation actually moves, and now both the crown and the root are heading in the right direction, but the crown is still moving a lot faster. This right here, this is the sweet spot for moving a tooth in a straight line. It's called bodily movement, or translation. When the counter moment from the couple perfectly balances the tipping moment from the force, the ratio is 1. All the rotational stuff cancels out, and the tooth just glides, with the crown and root moving together perfectly.
But what if we make our counter moment even stronger than the tipping moment? Well, now we're really in control. We've completely overpowered the natural tipping, and we get what's called root torque. In this case, the root actually moves farther than the crown. This is how orthodontists fine-tune the final angle of a tooth with incredible precision.
So that's the physics behind it all. Pretty cool, right? But how does this actually get applied in the real world with the braces you see every day? Well, let's start with a detail you might never think about: the width of the bracket itself.
The brackets that get bonded to the teeth aren't all one size fits all. They come in different widths, and this decision, wide versus narrow, has massive consequences for the mechanics. A wider bracket just creates a whole different system of levers. So how does that affect control?
Okay, so why go wide? Well, a wider bracket gives you a better two-point contact with the wire. It acts like a longer wrench. You get more leverage. That means it's easier to generate that controlling couple we need to keep the root where we want it. It also creates a smoother angle for the wire, which means less friction, making it way easier to slide teeth along that wire.
But
And this is a huge but. There's a major trade-off. If your brackets are wider, the space between them gets smaller. That shorter piece of wire becomes way stiffer, and its range of action shrinks dramatically. So for the very first stage of treatment, when you're trying to unravel really crooked teeth, wide brackets are actually pretty inefficient. So you can see the trade-offs right here. Wide brackets give you fantastic root control and are great for sliding mechanics, which makes them perfect for later stages like closing spaces. But narrow brackets give the wire more flexibility, which is a massive advantage when you're just starting out. It all depends on what you're trying to accomplish at that exact moment.
All right, let's zoom in even closer on the bracket. The next piece of this mechanical puzzle is the size of the slot, that tiny little rectangular hole where the arch wire actually sits.
The two main standards in the industry are the 18 mil slot, that's 18 thousandths of an inch, and the 22 mil slot. We are literally talking about a difference smaller than the width of a human hair. So does 4 thousandths of an inch really matter? Oh, you better believe it does.
The 22 mil slot is the original. It was designed by the legendary Edward Angle way back when they were using much softer gold wires. With the super stiff steel wires we use today, that larger slot means there's a lot more clearance, a lot more slop. The biggest advantage of that extra room is less friction, which is fantastic when you're sliding teeth down the wire to close a gap.
But here's the catch with all that extra room. That sloppy fit means the wire can't really get a good grip on the inside of the slot. So when an orthodontist tries to twist the wire to create that super important couple for root torque, there's just too much play. It makes getting precise control of the root incredibly difficult.
And that's why the 18 mil slot was developed. It provides a much snugger fit for steel wires, which gives you way better torque control, but at the cost of more friction. The 22 mil system is still incredibly popular today, but that's largely thanks to modern materials. We now have amazing titanium alloy wires that are big enough to fill that 22 mil slot for good torque, but they're so flexible they don't create dangerously high forces. It's a whole system that has to work together.
So as you can see, modern orthodontics is just this masterclass in applied physics. It's all a delicate balance of forces and moments and materials. But that's only half the picture. The real question to think about is, what happens when you combine this incredibly intricate mechanical system with the wild complexities of human biology and the predictive power of AI? That's where the future is heading, and that's where things get really fascinating.